Measurement of a stage. The stage of a river is defined as its water surface elevation measured above a datum. The air datum can be the mean sea level or the MSL or any arbitrary datum connected independently to the mean sea level. We have manual gauges. A simple and inexpensive. They have to be read at frequent intervals to define the variation of a stage with time accurately. We have two types of manual gauges. The staff gauge. The simplest stage measurements are made by recording the rise of the water surface in contact with a fixed staff. This staff comprises a durable material with a low coefficient of expansion relative to temperature and moisture. Next is the wire gauge. It is a gauge used to measure the elevation of the water surface above the surface, such as from a bridge or similar structure. The scope of this type of gauge is approximately 25 meters. Aside from manual gauges, we also have automatic stage recorders that overcome the basic objection of manual staff gauges and find substantial use in the practice of flow measurement. We have two typical automatic recorders. First is the float gauge recorder. It is the type of automatic stage recorder that is most used. In this case, a float operating in a steering well is balanced by means of a counterweight over the pulley of a recorder. Second is the bubble gauge. In this gauge, compressed air or gas is produced to flow at a very low rate through an outlet placed at the bottom of the river. Stage data is often presented in the form of a plot of a stage against chronological time known as stage hydrograph. Next topic is the measurement of velocity. To measure this, we have the current meters, the most commonly used instrument in hydrometry to measure the velocity at a point in the flow cross section. Two main types of current meters. Vertical axis meters. These instruments consist of a series of conical caps mounted around a vertical axis. And horizontal axis meters. These instruments consist of a propeller mounted at the end of horizontal shaft. A current meter is so designed that its rotation speed varies linearly with the stream velocity v at the location of the instrument. A typical relationship is v is equals to a times n sub s plus b, where v is the stream velocity of the instrument location in meter per second, and the n sub s is the revolutions per second of the meter, while a and b are constants of the meter. Typical values of A and B for standard size 12.5 centimeter diameter price meter is A is equals to 0.65 and B is equals to 0.03. Smaller meters of 5 centimeter diameter cup assembly called pygmy meters run faster and are useful in measuring small velocities. The values of the meter constants for them are of the order of A is equals to 0.30 and B is equals to 0.003. Calibration. The relation between the stream velocity and the revolutions per second of the meter, as in equation 4.1, is called the calibration equation. The calibration equation is unique to each instrument and is determined by towing the instrument in a special tank. A towing tank is a long channel containing still water with arrangements for moving a carriage longitudinally over its surface at constant speed. Field use. The velocity distribution in a stream across a vertical section is logarithmic in nature. In a rough turbulent flow, the velocity distribution is given by this equation, where v is equals to the velocity at a point y above the bed, v is the shear velocity, and k sub s is the equivalent sand grain roughness. To accurately determine the average velocity in a vertical section, one has to measure the velocity at a large number of points on the vertical. Simplified procedures have been cited below. In shallow streams of depth up to about 3.0 meters, the velocity measured at zero point 0.6 times the depth of flow below the water surface is taken as the average velocity in the vertical. Average velocity is equals to v sub zero point 0.6. This produce is known as single point observation method. In moderately kept streams, the velocity is observed at 2 points. First point is at zero point 0.2 times the depth of flow below the free surface. Second point is at zero point 0.8 times the depth of flow below the free surface. The average velocity in the vertical is taken as the average velocity is equals to v sub zero point 0.2 plus v sub zero point 0.8 all over 2. In rivers having flood flows, only the surface velocity is measured within a depth of about zero point 0.5 meters below the surface. The average velocity is obtained by using a reduction factor k, as the average velocity is equals to k times surface velocity. The value of k is obtained from observations at lower stages and lie in the range of 0.85 to 0.95. Sounding weights. Current meters are weighted down by lead weights called sounding weights to enable them to be positioned in a stable manner at the required location in flowing water. It comes in different sizes, and the minimum weight is estimated as W is equals to 50 times V times D, where W is equals to minimum weight in Newton, V is the average stream velocity in the vertical in meter per second, and D is the depth of flow at the vertical in meters. Velocity measurement by floats. A floating object on the surface of a stream when time can yield the surface velocity by the relation v sub s is equals to s over t, where s is the distance traveled in time. Next topic is the area velocity method. This method of discharge measurement consists essentially of measuring the area of cross section of the river at a selected section called the gauging site and measuring the velocity of flow through the cross sectional area. Calculation of discharge. Figure 0.14 shows the cross section of a river in which n-1 verticals are drawn. The velocity average over the vertical at each section is known. Considering the total area to be divided into n-1 segments, the total discharge is calculated by the method of mid-sections as follows. So this is the formula. For the first and last sections, the segments are taken to have triangular areas and area calculated as change in a sub 1 is equals to W sub 1 times Y sub 1. Example, the data pertaining to a stream gauging operation at a gauging site are given below. The rating equation of the current meter is V is equals to 0.51 plus 0.03 over S, where N sub S is equal to revolutions per second. Calculate the discharge in the stream. Solution. The calculations are performed in a tabular form. For the first and last sections, we have the average width W is equal to the quantity of 1 plus 2 over 2 raised to 2 all over 2 times 1, which is equals to 2.0 meters. For the rest of the segments, we have W is equal to the quantity of 2 over 2 plus 2 over 2, which is equals to 2.0 meters. Since the velocity is measured at zero point 0.6 depth, the measure the measured velocity is the average velocity at that vertical. So the discharge in the stream is equals to 6.454 meter cube per second. Moving boat method. In this method, a special propeller type current meter, which is free to move about a vertical axis, is towed in a boat at a velocity v sub b at right angles to the stream flow. If the flow velocity is v sub f, the meter will align itself in the direction of the resultant velocity v sub r, making an angle with the direction of the boat. Further, the meter will register the velocity v sub r. If V sub B is normal to V sub F, we have V sub B is equals to the resultant velocity times cosine theta, and V sub F is equals to the resultant velocity times sine theta. If the time of transit between two verticals is change in time, then the width between the two verticals is W is equals to V sub B times change in time. The flow in the sub-area between two verticals I and I plus 1 where the depths are y sub 1 and y sub I plus 1 respectively by assuming the current meter to measure the average velocity in the vertical. Here is the equations. Thus, by measuring the depths y sub I, velocity v sub r, and theta, in a reach and the time taken across the reach change in time, the discharge in the sub-area can be determined. The summation of the partial discharges, change in Q sub I over the whole width of the stream gives the stream discharge. Q is equals the summation of change in Q sub I. That's all. Thank you. That's all. Thank you.